In the last video, we talked about the properties and the definition of the logarithm, in particular of the natural logarithm, but these apply to all log functions. Now what we want to do is we want to derive the derivative formula for the natural log, and then go on to derive the derivative formulas for arbitrary logs with other bases. Okay, so an important part of this is going to be to look at this limit as v approaches 0 of the quantity 1 plus v raised to the 1 over v. We don't have a really good way of looking at that right now, but we'll look at some numerical evidence for this. And you want to keep in mind that e is the number is approximately, I should have here, is 2.718281828. Don't be misled. The 1828 does not repeat. It just happens twice there in this instant. And so now what let's do is I'm going to look at this for different values. So we'll take values, remember v is approaching 0, so we'll take values bigger than 0. So let's take a look at this when v is equal to 1. If v is equal to 1, notice this is going to be 1 plus 1. V is 1, 1 plus 1, raised to the 1 over 1, raised to the 1. 1 plus 1, 2 raised to the first power is 2. If we would go down the line here and look at this, for values of v that are getting closer and closer to 0, but from the right, because these are values bigger than 0, notice that this value of 1 plus v to the 1 over v is getting closer and closer to e. If we use values of v that are negative but get closer and closer to 0, all right, notice we start here with negative 0.1. I can't start with negative 1 because this would, if the v were negative 1, this would be 0 raised to the negative first, and that would be 1 over 0, which is undefined. But if we start at negative 0.1 and get closer and closer to 0, notice again those values of 1 plus v to the 1 over v get closer and closer to e. So this limit, as it turns out, this limit is going to be e. That's going to be an important thing. This limit is e. All right, now with that limit in hand, keep that in mind. With that limit in hand, let's take a look at the derivative of the natural log. All right, to take this derivative, we'll go back to the definition. And remember, the definition was the limit as h approaches 0 of the change in the function value, and that would be the natural log of, well, the natural log of x with each instance of x replaced by x plus h, the natural log evaluated at x plus h, minus the natural log evaluated at x, this would be the change in the natural log value, the change in the function value, divided by the change in x, which is simply h. As x goes from x to x plus h, it changes by h. Now we're going to use a few properties of the things that we recall, and so this would become the limit as h approaches 0 of, well, instead of dividing by h, I could multiply by 1 over h, and then the natural log of this difference here, the natural log of the difference is I should say the difference of the natural logs is the natural log of the quotient. So this would be, we could combine these using the properties of natural log or of logarithms in general, and this would be the natural log of x plus h divided by x. Okay. All right, now we want to make a couple of little algebraic changes here. This is going to be the limit as, and this is a little bit of creative algebra. What I'm going to do is I'm going to multiply this by x over x, but in this form, it would be 1 over x times, all right, x over h. Notice if I multiplied those together, I just get 1 over h, so I haven't really changed anything. And this is the natural log of, well, I have x over x plus h over x. X over x is 1, so it's 1 plus h over x. Then this first factor, 1 over x, does not at all depend on h. So as h approaches 0, 1 over x remains the same. So it's a constant factor, and I can take that out of the limit. Okay, and then I'm left with this limit as h approaches 0 of, well, I can write this as the natural log of 1 plus h over x, all right, to the x over h. Using the property of log, I can bring this x over h in as an exponent. And now, because log is a continuous function, provided this expression goes to a positive number, it's continuous for all positive numbers, it's continuous on its domain, I can take the limit inside of here because of the continuity. Okay? And so this would become 1 over x times the natural log of the limit as h approaches 0 of 1 plus h over x to the x over h. And now I'm going to make a substitution. I'm going to let h over x be v. Then that implies then that 1 over v is x over h. So this exponent is 1 over v. And that also implies that if I look at the limit as h approaches 0 of v, that's equal to the limit as h approaches 0 of h over x, which is equal to the limit as h approaches 0 of 1 over x times h. The 1 over x comes out of the limit, and so I just have 1 over x times the limit as h approaches 0 of h, which is 0. So this is 0. So notice that as h approaches 0, we have that v approaches 0. Okay, so we can rewrite this limit, making those changes, 1 over x times the natural log of the limit. Well, remember, as h approaches 0, v approaches 0, times of this limit of 1 plus h over x is v, and x over h is 1 over v. And from above, we saw that that limit was e, so this is 1 over x times the natural log of e. All right, now recall that if y, well, let's see, if y equals the natural log of e, then y is equal to the log base e of e. All right, so writing this in exponential form, e is equal to e to the y. Well, the only way that could happen is if y is equal to 1. So this is going to be 1 over x times 1, or just 1 over x. So as a result, we have this important derivative formula. The derivative with respect to x of the natural log of x is 1 over x. Okay, and now what we'll do in the next video, we'll go on to talk about the derivatives of arbitrary functions, and then later we'll use these to calculate the derivatives of more complicated functions.